To finish up our discussion on transmission line theory, I want to spend a couple minutes now talking about power transmission on a T-line. So to start with that, I'm just going to draw a transmission line. And we've got a T-line for which we've developed a pretty robust mathematical explanation now. And that transmission line is connected to a load, ZL. It can be a complex number. It can have a load resistance plus a JX, so that X can be a capacitance or an inductance. And for a lossless transmission line, so in the idealized case, we've got a I bar of Z, and we've got a voltage along the length of the transmission line as plus minus V bar of Z. And the expression for power at any point along the transmission line, P of Z, and we're going to be interested in this case in RMS power or average power, is going to be 1/2 the real portion of V bar Z times I bar of Z, and we're going to take the complex conjugate of that number. And both V bar of Z and I bar of Z in this notation must be in peak form. They have to be the peak phasor form, not the RMS phasor form, because we have this 1/2 outside. If these were in RMS, we wouldn't use this 1/2. So let's begin to analyze this situation. And I want to start just by writing out the complete expression for the voltage phasor notation. And that is equal to V bar plus times e to the minus j beta z plus the reflection coefficient at the load times e to the plus j beta z. So that's the voltage expression. And the current expression for current along the transmission line is I of Z is equal to V bar plus divided by Z, 0, times e to the minus j beta z minus the reflection coefficient at the load, e to the plus j beta z. So we've got voltage and current, and what we have to do is we have to just plug those into here. Now the math here gets a little tricky, so to simplify the math, I'm going to do one more step for both these voltage and current expressions. And that is that I'm going to distribute the V bar plus into the parentheses. So we get V bar plus e to the minus j beta z plus V bar plus reflection coefficient at the load, e to the plus j beta z. I'll do the same for the current. I bar of z is equal to V bar plus over z0, e to the minus j beta z plus minus V bar plus over z0 reflection coefficient at the load, e to the plus j beta z. And the reason I do that is I want to isolate what we'll call the incident voltage. This is the voltage waveform headed that direction. We'll just call it V bar I of Z. And then this is the reflected voltage. It's the voltage going back that direction. Back in that direction. And so that's V reverse in Z or V reflected in Z, whatever you prefer. And then the same arrangement exists for the current. This is going to be I bar incident of Z, and this is going to be I bar reflected of Z. And that technique allows us to disassociate the voltage into its two constituents and the current into its constituents, and then it also allows us to calculate power as either a power average, it's going to be equal to the sum of an incident power. Sorry, there's no bar over power. Power is not a vector quantity. It's going to be the incident power plus the reflected power. So to calculate reflected power, to calculate incident power, we're going to take PI average. That's just going to be equal to 1/2 the real portion of V bar incident of Z times I bar incident of Z complex conjugate. So we can substitute these two equations into here. So that's equal to 1/2 times the real portion of V bar plus e to the minus j beta z. So that's the first term. Then we need to multiply it by I bar incident of z, which is just this term right here, V bar plus over z0 e to the j beta z. But we can't forget to take the complex conjugate of that. So we can do a little bit of math. We get P incident average is equal to, okay, well this we need to multiply out V bar plus times V bar plus. The other thing to notice is that this is a complex number, so it's got a magnitude and an angle. Actually, so does the impedance under most situations. So we could write both those numbers in their exponential form. And we'll do that because that allows us to easily take the complex conjugate. So substituting in, we get V bar plus, the magnitude of V bar plus e to the j theta v, e to the minus j beta z. Now we need to multiply that by the magnitude of V bar plus over e to the j theta v divided by z0. And then we need to multiply that by e to the j beta z. Getting a little crowded there, sorry. So this operation real, it means take the real portion of things, and in this expression the only parts that will have a non-real portion are anything with an e to the j term in it. So we can pull out everything that doesn't have an exponential j term in it, and that's going to be 1/2 times, we've got magnitude of V bar plus times the magnitude of V bar plus, which is just V bar plus magnitude squared. We've got a z0 here, magnitude of z0. Real portion of e to the j theta v e to the minus j beta z times e to the j theta v e to the, we're going to pull this up, e to the minus j theta, and then we've got e to the j beta z. Star. And looking at that, I've actually made a mistake someplace. There's a minus sign right there that I left off. So plug in those minus signs. There we go. So that's correct. So we've got the complex conjugate. So how do we take the complex conjugate of that? Well, we just flip the signs on these guys. So just so you recall, a e to the j theta. If you want to take the complex conjugate of that, it's a e to the minus j theta. If you had a at angle theta, the complex conjugate of that is a at an angle of minus theta. And if you had a plus jb, complex conjugate of that is a minus jb. So we're going to use this format of the complex conjugate. That gives us the incident average power is equal to 1/2 V bar plus squared over the magnitude of z0 times the real portion of e to the j theta v e to the minus j beta z times e to the minus j theta v e to the plus j theta e to the plus j beta z. And that's nice because this term is going to cancel with this term, and this term is going to cancel with this term, leaving only the e to the j theta term. So we're left with the incident average power is equal to 1/2 V bar plus over z0 times the real portion of e to the j theta. Now e to the j theta, using Euler's identity, is just cosine theta plus j sine theta. So if we were to distribute that out all the way, we would take the real portion of this term and we would just be left with 1/2 magnitude of v bar plus over magnitude of z0 times the cosine of theta. Well, theta is the angle of the load, or theta is the angle of z0, and in a lossless transmission line, z0 is just purely real. So there is no theta, there is no phase angle between this and this, and so cosine theta goes to 1, and so the incident power is therefore equal to v bar plus, I keep losing terms here, sorry, v bar plus squared over 2 magnitude of the characteristic impedance of the transmission line. So that is the power incident on a lossless transmission line. We could do the math for a lossy transmission line. It takes a little bit of time, so I'll leave that up to you if you're interested in doing it. But the reflective power, we'd also be interested in calculating that. I'll save us the math on that one as well, and I'm just going to give you the answer, and it's minus 1/2 v bar plus squared over the magnitude of z0 times the magnitude of the reflection coefficient at the load. So those are our two formulas for power, this being the incident power and this being the reflected power. Well, the power on the line is going to be the sum of those two powers, the incident and the reflected power. So power on the line average is going to be PI average plus PR average. And you can see that both of these have this v bar plus squared over 2z0 term out, so we'll pull that out, and that becomes v bar plus squared over 2 magnitude of z0, and so that would be 1 minus the magnitude of the reflection coefficient at the load. And this is for a lossless transmission line. These are the three formulas. We've got the incident power wave, we've got the reflected power wave, and then the sum of the incident and the reflected gives us total power along the transmission line. So this is actually going to be power delivered to the load right here.